All right, so let me introduce our next speaker. It's my great pleasure to introduce Keshav. Keshav is the Robert Sanson Professor of Computing Science at the Department of Computer Science and Technology at the University of Cambridge. He was at the University of Waterloo from 2003 to 2019, holding a Canada Research Chair and the CSWIR Chair in Smart Grid. Keshav is a Fellow of Royal Society of Canada, ACM, and IEEE, and a distinguished alumnus of IIT Delhi. The recipient of two Test of Time awards from ACM SIGCOMM, Best Paper Awards from ACM SIGCOMM, Mobicom, and eEnergy. He's also the author of two graduate textbooks on computer networking and has served as the chair of ACM SIGCOMM. With that, I'll ask Keshav to present his screen, and we'll be looking forward to start.
Thanks, Ahmed. Let me see if I can find my Firefox. There we go. Share. Is this okay?
So we can.
Can you see my?
We can see it, but it's not a full screen. It's a very small window.
Oh, let me see. I'm sharing Firefox. Is this showing the slides or?
Yeah, I can see the slide, but the thing is that it's small for some reason.
It's small.
Yeah.
Is this better?
Yeah.
I can make it bigger too, I suppose. I don't know why it's supposed to be. Okay.
Maybe if you click on full screen, that might help.
If I can go full screen, sure. Yeah, I guess I should. Let me just clear all my other windows and I see make it full screen here. Yeah, that's a good point. Okay, I'll just make it full screen on this one. Is that better?
Yes. Now we can see that. Yeah. Yes.
Okay, great. All right. Okay. Thanks, Amit. I should add that I've known Amit for quite a while since he was actually my PhD student. So when I was at Waterloo. Okay, so we both moved on. The talk I'm going to give today is actually work that was done by Yurbal Osat, who was a master's student working with me, who graduated last year, and Ansis Rasmanis was a postdoc also working with me at Waterloo, and myself. And this was done last year when I was at Waterloo. And the reason I wanted to give this talk is actually two things. One is that I like the fact that it combines a certain amount of mathematical precision and a real operating system, similar to what Dan talked about, where he was talking about a programming language abstraction. Here to actually show you a control abstraction and optimization abstraction and how it can be implemented in practice. And also, this actually work has not yet been published, so I think it's kind of a preview of something that we're going to be sending for publication soon. So it has to do with the power efficient lighting control system. With that introduction, let me just dive right in. So lighting accounts for a lot of electrical power consumption, about 30% in buildings. As you can imagine, a skyscraper such as this, which has lots of rooms, also consumes a lot of energy for lighting. Now, there has been substantial improvement in the last few years, in the last decade or so. When you go from incandescent to compact fluorescent to CFL to LEDs, the ratio of energy usage is roughly 10:2:1. So there's a significant gain going to CFL. And most spaces, office spaces, are in fact using CFL. But LEDs gives you another factor of half in energy consumption and are widely used. And so one might say, well, if you already have this, then why do you need anything more? You already got LEDs and they've already saved you quite a bit. Are you done? The answer is that, sorry, I wanted to talk a little bit about here. So so I wanted to talk about the lighting efficiency. On the left-hand side chart of this, we see that the LEDs are improving in their performance all the time. So we're at 2020, which is over here. I think my mouse can be seen, and but we haven't fully reached the asymptote of efficiency for LEDs. In fact, they'll continue to increase, whereas the CFL and incandescent are pretty much flatlined. And consequently, the LEDs are widely being adopted, and the price is also coming down. So by 2020, LEDs will be slightly more expensive, In the next few years, in fact, they'll be overtaking CFL and LED. So are we done? And the answer is we can actually further reduce energy consumption by making use of occupancy detection, for example. So in this office, all the lights are on, but there's nobody there, right? So the lights aren't really particularly helpful. You might want a certain low level of illumination in order to not bump into stuff as you're walking around, but you don't need all this level of lighting. And similarly, if you have daylight coming in from outside, like shown over here, you also have the opportunity to reduce your lights because you have a lot of light, sunshine available. So this is what's called daylight harvesting. So the bottom line is if you're able to do daylight harvesting and occupancy detection, we can save about 40% more on LED usage as well. So what our goals, therefore, are to save energy, and but we want to do it in a personalized lighting comfort way. So each person should get the lighting that they want. So some people want brighter light, some people less light. We want to take that into account. We want to be robust to modeling errors. I'll talk more about that in a minute. And we want this to be responsive. So the sun goes behind some clouds. We want the lights to brighten up right away. And if the sun comes out again, we want to dim right away. And then we want to make it plug and play because one of the biggest issues with lighting, in fact, deploying any system in the field is that nobody wants to change. They don't want to have to change how they do things. And so what we want to do is the ability to somehow drop into what's already there. So this is what we envision. So imagine that there's an office such as this, which is in this case, a shared office, and there are some existing light fixtures like this. We want to just take those light fixtures, take them out and put in new light fixtures, which happen to be smart light fixtures. And this is not a dream. You can go buy them today. For example, the Philips Hue light fixture, which I'll show in a few minutes. In fact, you can drop it in, and they have inside them a Zigbee control module, and they can be controlled using software. And so what we want is to then measure the amount of light available on each desktop using the sensing module. And the sensing module reports to some controller, which I'll show you in a bit. And the controller says, oh, this is how much light there is present over here. It's overlit. Let me dim some lights. Now, of course, should I dim this light or this light or this light? It depends, right? It all depends on what we want for each of them. And so changing the dimming level of any one of these luminaires or bulbs has an impact on everybody's lighting comfort. So we have to do it very carefully. And also, if the sun comes out and you get more lighting over here, we can dim this one, but that one still has to be lit. Okay, so our problem formulation, therefore, is to control the lighting levels of each of these lights such that each desktop is properly lit according to their preferences. So the way we do it, I'll show you first a picture of our lab. So that's our lab, and we have over here a false ceiling that we built, and it has over here 8 LED lights, and these are all Philips Hue lights, which look like this. There's M of them. In this case, M is 8, and then these shared workspaces. Is the 4 workspaces over here, and on this over here is our measurement unit. It's just a small, what's called an Onion Omega single board computer with a light sensor and an occupancy sensor. And all of these are reporting to a controller, which is a Raspberry Pi, which is actually this one, this box right here that I'm circling over here. And that controls something called the Philips Hue bridge through a software API, and that controls LED bulbs. So we can control this over here. So I'd like to actually show you a brief demo of how the system works. And so there's my smiles. This is actually on YouTube, so I'll play it over here. So this is I want to show what happens when occupancy changes. So here's my student. Yurbal is sitting at the desk, and this matrix on the right-hand side, basically it has 4 values. 1 means it's occupied, 0 means it's not occupied. And because he moved, you see 1, 1, and then the others are 0, 0. And what you see over here is the lighting level we want is 450 lux. And he's getting 450 lux at each of the places where he's sitting. And so as he moves around and the occupancy changes, the lighting level changes to match the 450 that he wants. And when he stops moving, what happens is the lights start dimming again. And what you're seeing over here is basically it's responsive to his occupancy. The lights are changing. So we're getting the occupancy detection, the responsiveness. What happens if the sun comes out? Well, in this office, there is no sun. So we're going to fake it by using this lamp over here. And what you see is that we want to have a required level of 250 in this case. And as the sun comes out on the lower left, you'll see that it becomes essentially maintains 250 even though the sun is out. So what's happening is they're dimming in response to that. And so the system quickly responds, and we'll measure this. It about takes about 1.5 seconds to respond to this. And then here we want to show that different people want different preferences. So some people want 450 on the left, 450 on the left-hand side and 400 on the right-hand side. You can see the matrix, there are measured values of 450 and 400. And when you have a sudden change, you turn on the lab lights, it takes, again, a little bit to respond. And then what happens is that it actually it gets to the right level again. So this is an example of how the system works. And we can actually do this anywhere. We can go to any location, just remove the bulbs, put in these Philips Hue bulbs, and then install these sensing modules, which are about 3 centimeters by 1.5 centimeters approximately, really small modules that are powered by USB. Okay, so it looks pretty simple. So let me show you what the problems are, because so this is what we want to do. We want to minimize the power and subject to the lighting level meeting some target, and the dimming levels are subject to some of the conditions. So I find that when people do presentations, they show a slide like this and they say, well, of course you understand it. And the problem is, I'm kind of stupid. I don't understand it. So I'm going to walk you through it very step by step. So first, DJ is for each bulb we call bulb J. So J goes from 1 to N, the N, 1 to N bulbs. And what we're going to do is we're saying that we're going to choose the dimming level between 0 and 1. That's what we have over here. And then when the dimming level is DJ, then the power value that it has, the power it consumes is P of DJ. So obviously when it's fully lit, it consumes more power. And when it has not lit, it's less power. So that means we want to reduce the total power. We want to choose D, the vector bold D, which is the vector of dimming levels, such that the power is minimized. So, okay, so that makes sense. What about the other stuff? Okay, so that's the power cost. It's saying at location I, so the ith workstation, we want to know the illumination, which is called R sub I, and at when the dimming level is D and at time T. Okay, so the thing is the illumination is going to keep changing because the sun will come out and the sun will go away. So R keeps changing. And we're saying that that's the minimum we want. The minimum level we want is 8 sub I. And so because of user preference, it's going to be different for each location and occupancy. So if it's not occupied, we'll set this to 0, because we want this to be, essentially we want this to be greater than or equal to 0. Any number greater than 0 is fine. But if you want a slight level of illumination for the night level, you can say HI is, I don't know, 5 lux, something like that. And now this equation hopefully is a bit more easier to understand. Okay, so, but the problem is, what is the power cost of dimming? When you dim, how do you know what that is? And second, how do you know the illumination corresponding to dimming level? We're not saying measure the illuminance just as a meter. We want to have it as a function of D. And how is that function computed? Because we need to figure that out. So let's start with the first one. So power versus dimming level. We can do that experimentally, right? So what we do is we take the bulb, just choose a certain dimming level of the bulb, let's say 20%, and we measure the power that it used, and then use 40% power that it used, etc., all the way up. And it is, of course, going all the way up like this. But we notice that when the dimming level is 0, it still consumes non-zero power, and that's for the electronics. The Zigbee module inside it consumes some power, so that's going to be needed over here. And that introduces a nonlinearity at 0. And second, this is not exactly a straight line. It actually has a slight dampening of the curve. And so, however, these nonlinearities make the optimization problem that we're going to solve in a minute very complicated. So we're going to linearize it. We're going to use this green line instead and pretend that it's linear, and actually we'll have the green line going down to 0. So in fact, we're going to assume that it goes through 0, 0, rather than with this offset over here. And so, so initially we would just say 11.8 DJ plus 1.8, and then the next step we'll get rid of this, which I'll show in a minute. And at that point, we get a completely linear formulation. The second thing is that, so here when you take this, we had this equation, we're going to replace that by saying, look, it's linear, so let's not use P of DJ, we'll just do DJ, and then everything else remains the same. The second thing is that the software that we get doesn't allow us to control the dimming level directly. Instead, what we get is a brightness control value B, which goes from 0 to 255. And so what we need to do is to actually figure out for a dimming level control value, what is the actual dimming level. And so we looked at 7 bulbs, and we did 2 experiments with each bulb, and we measured it. And you can find that for all the 14 experiments, there's a very, very identical mapping from the control value to the dimming level. And in fact, we can fit it to this equation over here. It's 2.64 into this one over here. And so we do have a ability to choose a B value. So if you invert it, we know what B value to use for a particular D level. Again, we're not just relying on one bulb, we're doing it for a whole bunch of bulbs, and using for this one, we're able to replicate that quite exactly. So the system model then becomes something like this. We want to essentially say that this illuminance over here that we're seeing at light level that we have over here, where is it coming from? We're saying it comes from two things. One is it comes from the bulbs themselves. So this is the dimming level of the Jth bulb, and then we have this matrix called the Aij illuminance gains matrix, or the transfer matrix. And what it says is that if bulb J is lit, then the ith workstation will get dj times aij illuminance from it. So you can think of it as the transfer function of the signal, the light signal, from the source on the receiver. And so the sum of this tells us for the ith workstation, the summation across all the different bulbs, j equals 1 to m, using this matrix tells us the contribution of the jth bulb to the R. And then this E sub I is the light from elsewhere. It's all of the light from the windows, for example. So the total illuminance is the external illuminance plus the illuminance from the bulbs. So that's what this equation means over here. And so now the optimization problem, we're going to change it again. We had to replace this with DJ. Now we're going to substitute for R sub I, and we make it EI, outside external light at the I's desktop, plus this value over here, DJ AIJ. And then everything else remains the same. Okay. Right, so, but what about the matrix A, right? We have this over here, we just put in this, we don't know EI really, we also don't know AJ, so how can we estimate that? So we use a trick for doing that. And what we do is that we assume that the transfer matrix and environmental conditions do not change, and we slightly change the dimming level of one bulb. So we reduce it by, let's say, 10%. If you reduce one bulb by 10%, you basically can't see it at all. And then we say, okay, if this changed 10% over here, and if this went down by 1%, then AIJ must be 0.1, because the 10% change is attenuated by a factor of 10 coming over here. And so we know that AIJ is 0.1, right? If this change, 10% change over here results in 10% change over here, then we know that AIJ is 1, etc. So we can estimate every row of this and every column of this using by dimming of the bulbs one by one and looking at the recorded illuminance values before and after the change in dimming level. And more precisely, what we can do is we can look at the light sensor reading before and light sensor reading after, and we take the difference and divide it by the dimming step, and that tells us the illuminance gains estimate. Now it's estimate because there are going to be errors, of course, there always are measurement errors. And so here's an example for our building, for that room I showed you. We have 4 workstations and 8 bulbs, and this is the transfer matrix. And you can see, you can actually estimate or you can evaluate the transfer matrix precisely using this approach over here. Okay, so however, there is error. So we have the gains matrix with A tilde and the actual matrix A, and the difference between the two is epsilon. Epsilon is time varying because actually as the bulbs heat up, they produce a bit more light, for example. And also if somebody enters the room and leaves the room, there's going to be some extra reflection off of their body onto the sensor. And then so the A matrix changes, but we may not have actually measured it properly. So there's going to be a bunch of calibration errors and estimation errors due to the time varying nature of the transfer matrix. And so what we do is that we then essentially convert this problem. So we had to, remember we had to minimize the sum of the D subject to this. We're going to
sorry,
change it
Keshav.
Yeah.
Can I have a quick question? Just clarification
Yeah, go
question.
ahead.
The
Sure, yeah.
two slides previous when you estimate the A matrix.
Yes.
Yeah, so there's a much for each row. There's a sort of dominant entry, or maybe there are two
Yes.
in the third row.
Yes.
I
There
just
is.
wonder
Yes.
what that means.
The
Maybe
dominant
two
entry
in
is
the
a
fourth row.
closest bulb.
Oh, I see. But there are two dominant. Okay.
Yeah,
I
because
see.
you look
Okay.
at if you remember, there were these two workstations to the left, two to the right.
Oh, okay.
And then, so the dominant entries are the bulbs that are the closest. So 198 and 301 would be the two bulbs closest to that workstation.
I see. Okay, great. Thanks.
And then this one's 136, 329, and then the two on the right will have similar ones. So it all, it depends on the orientation. It's a very perceptive point, Stephen, but yeah, that is exactly yeah.
I see. So it depends on the distance, but also, I guess, maybe some kind of angle or something.
That's correct. Yeah, I
Some drops to
mean,
1.35, drops very rapidly.
say that again, please.
So it depends on the distance, but also maybe the orientation or something.
That's correct. I mean, you can imagine that a bulb that's very far away has almost no contribution at all.
I see. So, but but for example, the relationship between the distance and that's not important. You just get this matrix directly.
Exactly. So that's the beauty of it, right? Normally, when we do these kinds of things, the typical approach actually is to use a radiance model, which is a vector tracing model, right? Where we are able to trace the vector, the direct path and the reflected path. If you remember how people used to do wireless, here what's called the one ray and two ray models.
Right.
Here we are actually directly measuring at the recipient the received flux.
Right.
And so we don't need to use a ray model. We can actually, so this, we're actually doing a direct measurement of the transfer matrix.
Right. Okay, great. Thanks.
Yeah,
Sorry for interruption.
that's okay. So this is essentially identical to channel state indication, CSI measurement in Wi-Fi. If you look at 802.11n, this is exactly the CSI actually.
I see. Okay, thank you very much.
Sure, yeah, because we can think of each bulb as being a separate subchannel. And we have orthogonality due to photons. I mean, it's still electromagnetic spectrum, but we have non-interference because of photons non-interfering in the light regime, unlike interference in the radio regime. So it's pretty neat. There's a very clear mapping to Wi-Fi, actually. Anyway, I won't go down there. So here, remember, we had this summation. We had replaced R with ET plus AT. Now we're going to replace it with E minus A. We're going to replace as A tilde minus epsilon. Basically, that's what we're doing over here to the error that's going to happen. And the problem is we still don't know that. We still don't know the external interference. We still don't know the error. So what do? What we're going to do is we're going to go into an iterative control problem. So inside the optimization problem, or actually not inside, but outside the optimization problem, we put in a control problem, and we use model predictive control. And I'll explain what that is at a high level here, and the details are in a paper which I can send you. But the basic idea is that we have this K represents the kth iteration of the controller, and a model says that the received illuminance RK is the external illumination EK minus epsilon and plus A tilde. This is just the same thing as before. We just was AK plus DK AK. I put out the epsilon term separately. And what we're going to do is we assume that the error term doesn't change too quickly between model iterations. So if you're updating if you're doing the control actions fast enough, the error won't change too fast, and also the dimming value doesn't change too fast. And the environment doesn't change too fast. So if the system is relatively stable, then we will find that we can use the prior measured values of error, epsilon k minus 1, and the prior dimming level, dk minus 1, that we know to estimate what ek is right now. More specifically, ek is given by looking at the illuminance that you have last time minus what your model said illuminance should be, A tilde dk minus 1. So essentially what you're saying is that I'm seeing, let's say, 100 lux, according to my dimming bulbs, according to my bulbs and the transfer matrix prior, I should have been getting only 70. So where am I getting 30 more? Oh, the 30 more must be due to EK, external light, minus the errors, epsilon K minus 1, right? So you can estimate basically the external light by summing out what we know from what we actually see. So if we see 100, we're guessing there should be only 70, the rest must be due to the outside light. So we can estimate that. And I'm going to skip over the math. It's a little bit more, but essentially what we're going to do is we are now going to minimize the sum, where we essentially look at A tilde and the difference over here. And this becomes a completely linear problem over here, which can be solved using standard methods, where we are essentially using a relaxed model. The relaxed model meaning that we are assuming that the errors are not great, or I should say the difference in errors is not great. And maybe it's better to explain it this way. So here's what we're having over here. So we start with the LEDs in the middle, and we choose some dimming level D using the optimization problem. Okay, and the optimization problem says if the level is D and the target illuminance is H, and I'm seeing with R what the actual illuminance is, this is what I need to do for D. So that's what it's doing over here. The actual level of illuminance you're going to get is affected both by some delay and by the light sensors measuring some outside external value of E. And so this tells you the true value of R. So basically we have feedback control, which is wrapping around the optimization problem. And this feedback control is what's used to adjust the D so that you're achieving the target value greater than or equal to H. So that's in a nutshell what's going on. Again, the details are slightly complicated, but the intuition is that we can't use optimization alone because of measurement errors. So we need to drive down the errors using a control subsystem overlaid on top of the optimization. I think this general idea of mixing control and optimization is actually not particularly new. I mean, MPC does this all the time. However, MPC doesn't take into account model errors in the way that we do. And more specifically, we can actually show the convergence of dimming levels by looking at how the change in the dimming levels happens. So it's delta dk plus 1. And that's based on the pseudo inverse of the transfer matrix A tilde inverse. And if the A tilde inverse values are fairly large, in the range large, then actually, for example, it's 1,000. And being imprecise here, this is what I mean by 1,000. But if it's largish, then the error diminishes quickly. On the other hand, if you have if the size of the matrix is in the same level as the errors in the measurement, then we don't get convergence. Again, this is not surprising. Obviously, if you're going to have measurement errors that are comparable to the measurement values, then you can't really converge. Okay, so this we can actually show that as the change in the dimming levels goes to 0, that means you're getting closer and closer to the right value. In fact, we converge to the desired value H. We actually get to H pretty fast. Okay, so that's basically the idea over here. And so that's why I said it's optimization plus control. And by the way, the reason we were forced to do this is we started with the optimization problem, but we had sensors that weren't very good. The sensors actually were inaccurate, and we spent a lot of time figuring out what to do. And in the end, we were forced to adopt the control approach rather than just a pure optimization problem. We had to put in optimization control. And this is actually in the lighting literature, this is new as far as we know. Most people just say, well, we assume the sensors are perfect. And we're saying, well, we assume that the sensors are perfect, but we assume that we make measurement error. There are going to be some measurement errors. Obviously, if the sensors are off by a certain value, we can't correct for that. I mean, if the sensor says it's 200 lux, it's actually 300 lux, we're out of luck. But we can account for transient issues and any measurement issues in the estimation of the A tilde matrix. Okay, so just a few slides to show how it works. I want to first show you how response changes in daylight. So I'm showing two graphs. On the upper graph, you have showing on the y-axis is the illuminance in lux, and the x-axis is time. And we have chosen these four sensors. So we've chosen heterogeneous lighting comfort values of 300, 350, 450, and 500. And what happens is in the beginning, they all had the right values. And then when the green bar happens, what happens is we suddenly got extra light. Daylight came in. And so all of them became overly lit. But then in about 350 milliseconds to 2 seconds, approximately in that period of time, the control system kicks in and the lighting levels diminish to the desired values again. And when the light is switched off, again, there'll be a slight dimming, and then it comes back up again. So these values, this basically is reflected in these graphs over here. So there is slight dips, even though we have fairly abrupt transitions when you have the light come on. And the bottom level shows the dimming level controller, and you can see that when the light comes on, everybody's dimming levels goes down, all the bulbs dimming levels go down, and then they recover again when the light goes up. And so we spent quite a bit of time trying to reduce these delays, and so that's what we showed in the video. What about changes in target illuminance? So somebody may say, I want a brighter or I want a less bright environment, and the dashed line on top shows what they want. And so you can change it every few seconds even, and the system nicely tracks what you want to do. And this is the orange line is the line shown for the one thing that's changed. All the others are unaffected, as you can see, which is very cool. Everybody else has pretty much the same light, just the one side that says I want it brighter or dimmer. They're being controlled, they're matching approximately what they want, but the other workers in that cubicle office are unaffected by this. And then with the reduction in energy consumption, so we said, okay, we did all this work, how much energy did we actually save? And to solve this problem, we actually need to know couple of things. One is we need to know the average amount of daylight that comes in every office. And also we need to know the occupancy. And so we couldn't find any data set which measured the external daylight. And so what we did is I found some colleagues who were on sabbatical because I needed unoccupied offices. And so in 3 of these offices, we collected data for 7 months, every minute for 7 months. So we have a fairly large amount of data of the amount of daylight coming in 2 locations in 3 offices at Waterloo. And we also collected occupancy in a different set of offices over 3 years for a different project. And we sort of mixed these two together to find out the estimate, the amount of energy consumption we would reduce by using our system. And so the example of our data set looks something like this. The orange line shows the daylight that we measured. So, if there's no daylight at night, it's around 7 or 8, the sun comes up, it goes up and go down. There's some more clouds in the afternoon. And then the blue is the occupancy where people are coming and going. And the lower level is showing an occupancy of 0. There's nobody in that office that particular day. And we have actually open sourced all the data. So both the occupancy data and the light level data. The light level data was released last week. So it's in OMID's archive on energy.acm.org. And then the occupancy data will be releasing probably next week. So all of that is going to be available for anybody who wants it. We have collected 58,000 hours of occupancy across about 65 office rooms across about 3 years. So we have quite an extensive data set we're going to be releasing to the publicly. And so we simulated a bunch of different systems where we had occupancy or not. We had daylight harvesting, yes or no, and incandescent CFL LEDs, so a lot of different combinations. And this slide sums up pretty much everything that I said over here. If you have incandescent, you use about, for daily energy consumption, the y-axis, you use about almost 5 kilowatt hours for this particular office configuration. And CFL, if you just do basic CFL, you go down to 1.5, so a factor of 3x reduction. And if you go to LED basic, you get down from 1.5 to 0.85, so approximately another factor of 2x reduction in consumption. Now, if you just do LED and you just do occupancy detection, actually it goes up. And the reason is because the system that is using all the measurement and so on actually adds energy to the Wi-Fi system and so on is adding energy, so it goes up. But if you do daylight and occupancy detection and sort of smart lighting system, you go from 8.5 to zero point 0.5. It's about another 40% or so reduction in energy consumption. If you look at it overall, so we switch an office from incandescent to a smart system, we're getting approximately 10x reduction in energy consumption for lighting, which is actually pretty significant. Okay, so to sum up, this work is done, and all the software, all the data is open. Actually, all the software is available on Git as well. We'd like people to build on it, but there are some limitations. So if you remember, we did not use the Luminaire model. We linearized it, so we are using a relaxed model. So that's going to result in some error. There's an estimation error in the illuminance gains matrix. That is unfortunately something we're going to always have. We arbitrarily chose the sensors to be slightly above the office desk location. Actually, we put them on top of the monitor because nobody's going to put anything on top of the monitor. It's a very thin location. But where is the best location for sensors is an open question. And in future work, we could control the daylight that enters the room by controlling blinds. We haven't done that. And as of now, we don't have any GUI for the users to control their preferences. So that's straightforward, but we haven't done it. Okay, that's pretty much all I had to say. Thank you.
Thanks, Keshav. Thanks, Keshav. For the great talk. I can hear my echo.
There seems to be a bad echo.
Yeah, I muted everyone just to make sure that.
Okay. Okay, that's fine now. Yeah, go ahead.
Okay.
Yeah.
Perfect. So, we have time for a couple of quick questions. I know that there are some questions in the chat, and a couple of people wanted to ask questions. So, please go ahead. I see one question in the chat by Sanju. Sanju, do you want to unmute yourself and ask it, or I can ask it quickly? So the question, let me ask it for the interest of time. The question is it necessary to have per desk sensing module, or can we have a common sensing module for the many desks in an office? And how does
Can we have a common sense?
Can we have a common sensing module for many desks in an office?
Oh, I see. Yes. Okay. Well, the thing is, if you want personalized comfort, then you need to have a sensor per person. So that's pretty obvious. If you have a common sensing module, then they need to share a common illuminance desire. And moreover, the sensors need to be placed where you want the light to be. So if you place a common sensor halfway in between, then that spot that's halfway in between will be well lit, but the two desk workstations may be dimly lit. I mean, that's a pathological case, but no, the sensors are very cheap. I mean, we're talking about, each sensor is about $8 or $10, so it's not super expensive.
Mm-hmm. So there's another question, Keshav, about the cost analysis that you mentioned, and also how long does it take for the extra investment to be to pay off the investment? So they're talking about the
that's a really good question. And we did do the analysis actually, but the problem is it is very site specific. It depends on what you pay for electricity in each jurisdiction. What you pay by day, what you pay by night. Also, it depends a lot on the occupancy and how it changes. So, if it's a shared office, is everybody present or not? How often are people present? It's very, very sensitive to occupancy, daylight, and electricity tariff. So we did the analysis, and then we realized, it's not particularly meaningful to talk about it because everything depends on these parameters, which are very hard to control. What's called the workload. It's very workload sensitive. So my guess is that at the moment, these systems will take probably 5 to 8 years to pay off. But it really, really depends. Are we going from incandescent to CFL? How many people are occupying? If you have a room which is very rarely occupied and it's left on all the time, then of course it will be paid off itself very soon. But and if it's a room which has no windows, then the daylight harvesting is not going to help you at all. So then you may as well just use a standard occupancy sensing PAR module. So it's kind of difficult to answer that question precisely.
So there is one last question, I guess, from Nico. Nico, would you like to unmute yourself and ask it?
Sure. Thanks for the interesting talk, Keshav. Very nice to learn something. I just have some question. Your talk reminds me a line of research on smart air conditioning system where also monitor the comfortness of building occupancy and try to control the aircon to provide comfort at the same time save energy. And I think your team has much work on that as well. And I was wondering, from your understanding, what is the key difference between like the smart lighting system and the smart HVAC system? Understand?
Okay, no, I think that's a great question. Okay, this is okay. So the distance between the two actually has to do with system memory. So HVAC system, when you turn on the cooling, it takes anywhere from 5 minutes to half an hour for you to have the impact that you want. So there's a considerable amount of inertia in the system, right? With light, there's zero inertia. It's beautiful. You turn the light on, there's no memory. It's very, very instantly controllable. So all the math becomes much, much easier. Whereas for any kind of HVAC system, these transients, especially if you're talking about chillers, air handling units, VAV control boxes, etc., it becomes really, really complicated. So lighting is much nicer that way.
Great.
Thank you.
Great. So, and one last question from Stephen Hill.
Sure.
Stephen, do you want to ask it yourself or?
Sure. Yeah. So, yeah, very nice. Thank you very much, Keshav. So, is it necessary to recalibrate the A matrix or is the LED very stable, so it's not necessary?
No, the A matrix is recalibrated every 10 seconds or so. And the reason is because we need to just think about it from the RF perspective, right? If you have any kind of mirror or reflection, if somebody wearing a white shirt enters the room, the A matrix changes, right? If somebody opens a window, somebody opens a door, the A matrix changes because you're going to get multipath reflection off of that. So we constantly recalibrate the A matrix, but the thing is, it's unobtrusive because we're going to change it by 10%, do each one for 10, and we can do, for 8 bulbs, we can do the whole A matrix calibration in about 10 seconds or so. And I can't remember the exact numbers, 10 seconds or 20 seconds, and we just recalibrate the A matrix because there's no particular reason why we can't do it. And that's another nice thing, by the way, compared to HVAC, where the transfer matrix, it's not exactly a transfer matrix. You have this fluid flow that you need to essentially resolve a computational fluid dynamics problem to estimate the impact of a certain change in the chiller temperature on each of the locations. Whereas here, we can actually directly estimate the A matrix by doing this unobtrusive calibration.
I see. Okay. Yeah, I somehow missed that. So it is in the background. You actually, I see.
Yeah. I mean, yeah, exactly. So we are doing that. Yeah, exactly.
Okay, great. Thank you.